Good afternoon, everyone. My name is Anil. I'm senior research scientist at IBM Research. And this is work together with my co-authors, without which none of this would have ever worked. So today we will be talking about how we can combine memory error exploitation with speculative execution attacks. So in order to do that, I would like to take a step back and take this quote from the language security community, so Sergey Bratis and friends, which to basically rephrase says that we need abstraction to build complex systems, but those abstractions create boundaries of competence, and essentially the attackers then exploit those misunderstandings between the layers, right? So I'd like to put that in the context of the work today. If we think about somebody writing a C program, right, or a higher level program even, they might not always be aware of that, what that means in terms of the assembly code that the CPU is eventually going to execute, or what the memory model is exactly, and that might lead to memory errors, for instance, right? So that's why people design memory safe languages, for instance, to avoid those kind of issues and abstract away that sort of reasoning from the programmer. Similarly, if we think now about Spectre-like attacks, those assembly instructions, from the point of view of the processor, they're not sequentially executed like the programmer might think, but at least on a modern superscalar processor, they will be executed based on some predictions and executed such that in order to execute more than one instruction per cycle, we will need to make some sacrifices, basically, that the programmer is not really aware of. And this leads to issues such as speculative execution attacks. So this talk will be about combining these two ideas and how we can combine it to great effect. And if there's one thing that, as an attacker, you would want to remember from this talk is that if you're stuck on a memory exploitation problem, maybe you want to think about using speculation. And if you're stuck exploiting some speculative execution attack, you might want to think about memory errors. So we're going to go through two specific papers, but before, a little bit of background on Spec. So this is essentially part of a Spec attack, right? We can have a piece of code inside of the vulnerable program, which will have a branch condition on an array size. And if we want to then load from this array indexed based on this attacker value X, if we think about the cache, and if we do that many times over and over, we will train inside of the CPU at the microarchitectural level, we will train the branch predictor such that it will always think that whenever we execute this code inside of the victim, the branch will be taken. So whenever we have the X that's out of bounds, for instance, indexing some secret data, the CPU will mispredict and will execute to load at that particular address that's attacker provided. So that's what we call conditional branch misprediction, right? In reality, though, this is not sufficient because that's just accessing the secret. And if you look at the original Spec paper, you need something that looks a little bit more like this, where you have a second array, which is actually going to be used to essentially achieve a side channel send. So we access some memory that's going to be later received by the attacker via a flush and reload attack. The problem with this is that it's pretty difficult to find such a pattern, although the previous pattern looked super generic and nice. This one is not. So we need to find typically other ideas if we want to exploit programs with Spectre. And one of the nice ideas was from this paper called essentially Speculative Buffer of Throws from Kiriansky and Walsprüger. And what they thought is, instead of doing a speculative load, what if we do a speculative write? So here we write inside of the array at index X, our attacker-controlled value val. And if we think about the stack, right, which is on the left-hand side there, so the stack goes down, we have our array at the bottom, and as we continue to write and we index higher up, we can override speculatively the return address. So what that means is that once we will hit the return during speculation, during transiently, we will be speculating on the particular address that was written by the attacker. So that means that during speculation, we obtain a control flow hijack primitive. This is not an architectural control flow hijack, to be sure. So it will have some limitations. It will be limited by the speculation window that's given by this misprediction before. But it still allows us to do arbitrary computation in the speculative domain. So can we use this attack further? And that's basically the topic of the first paper that I want to present today, where we looked at multiple things, but one of the first things that we started thinking about is, okay, if you have your classical buffer overflow, so in this case, it's a for loop, and we overwrite, let's say, the whole array with our attacker-controlled value. But let's say that we have some mitigation, and typically today, in most binaries, we will have stack cookies, right? And the question would be, can we bypass, right? Because if we think about the assembly code, so when we enter the function, we will store on the stack cookie. And when we will leave the function to check whether the stack cookie was corrupted, we will first check, we will first load the stack cookie from a safe area. Then we will load it from the stack. And then we will compare both of those values with the XOR here. And if they don't match, then we panic and we stop execution because we have detected a stack-based buffer overflow. So that's how stack cookies normally work. But as you see, that's a conditional branch once again. So if we remember from earlier, that's something that we can bypass, right? So we thought, okay, let's try to exploit this. And we looked at a specific case. We looked at some pre-existing vulnerability in libpng that was stack-based buffer overflow. Just at a high level, so there's this length that's attacker provided, and there's this read buff array, and eventually there's going to be a read into this read buff array, and it just so happens that there's a stack-based buffer overflow there, because the check is not sufficient. But this is caught by stack canaries, and there's basically no way of getting around it in classical terms. It's totally unexploitable apart from crashing the program. So we thought, okay, maybe we can use this, and we did. Implementing the attack in practice, however, took us a lot more than this basic idea. It was not so simple. So I'll explain a little bit the high-level ideas. And the most important step is this eviction step. As I said earlier, we need a speculation window to exist in order for us to do our speculative return-oriented programming with our gadgets inside of the program. So that meant that we had to build eviction set for the particular saved stack canary instead of the TLS. Then we need to get this memory to be reused by the victim program in reality. Then we can initialize also our side channel. So we will be using flush and reload via a shared library that's mapped in both victim and attacker. So this is basically any library that you will be using on the system across multiple processes will be shared, right? Similarly, we will do return-oriented programming via gadgets, and we will also train that at first before execution. So that's step number 2. Then we are ready to send our input that will trigger the buffer overflow architecturally, right? This buffer overflow will overwrite the return value and also the stack cookie, but speculatively, this will trigger the speculation window to start. That's because we will be evicting in the background as the attacker process in the meantime. That will mean that in the speculative domain, there will be the return-oriented programming gadgets that we prepared that will be executed by the victim in the speculative domain. And then we can leak the data into the attacker. So we've put all of these steps together, and we were able to leak arbitrary data from the victim program in this case. In fact, in the paper, there are many other cases that we looked at, because this is not the only, let's say, memory safety defense that one can bypass. One of the things that we talked about is that it would be nice to look at memory safe languages. And Go is one example of that, where we were able to demonstrate it in, let's say, specific cases, and we discussed it with the Go developers, and they included a particular spec flag, which then prevents the exploitation of those vulnerabilities using basically an SLH-like feature. And you might be able to then think, okay, if you can't do this, you can probably bypass any mitigation mechanism, but that's not true. We also tried with LLVM CFI, the control flow integrity mechanism implemented by the LLVM compiler. And that was not possible to bypass it because of the speculation window and how we would need to evict things. But we also looked at GCC's vtable verification, which is also another form of control flow integrity, and that was bypassable. So it entirely depends on the actual implementation, but it can be used in many, many contexts, and we have that in the paper if you're interested. So the other thing that I would like to talk about today, so we talked about exploiting spatial memory vulnerabilities such as buffer overflows, but what about temporal memory vulnerabilities such as use after freeze? Can we combine that with speculative execution attacks? So that's the topic of this second paper called Ghostrace. And let me start with some background on use after freeze, concurrent use after freeze more specifically. Let's assume we have shared data between multiple threads. So we have two objects. The first one, struct A, has a pointer to struct B. It might look like this in memory. And struct B would have, let's say, a function pointer. Let's assume that thread 1 will be executing in the following code that will be freeing essentially the pointer to struct B, so object B, and then setting up this pointer to null, right? And let's say we have a second thread that's concurrently trying to access the pointer B through struct A, and then execute the function call, right? So here there's a concurrency bug when we have both of these programs running, because let's assume that we arrive at this free. Here we interrupt thread A, then we make thread 2 run. Then make the attacker run before thread 2, and the attacker would allocate some memory. So that's the use after free part, and it would place in place of the function pointer, for instance, a pointer to exec v, such that we would spawn a shell when thread 2 executes, right? So that's a classical concurrent use after free attack. And the way to mitigate this, or to prevent this from ever happening, or the proper way of programming would be with synchronization primitives, right? So you would put, for example, mutexes in this case, around both critical sections, such that they never execute at the same time. Or in other words, whenever you're free, you will always set to null, such that the check of whether the pointer is null would always pass. Right, so that prevents the attack. And so it looks like this piece of code is bug-free and unexploitable once again. But what happens during speculative execution? So that's what we looked at. And indeed, you've guessed it, we can bypass it. Let's look at the mutex implementation inside of the Linux kernel. It's essentially a compare exchange instruction. What's important to know here is that just because it's atomic, that doesn't mean it's serializing in the eyes of speculative execution, right? So this conditional branch, we can once again bypass it and execute. So we did implement this in practice inside of the Linux kernel. So this whole class of attacks, we call them speculative race conditions, and there's potentially multiple one of those that you can have, but we looked at speculative concurrent use after free exploitation inside of the Linux kernel. So we found a piece of gadget using our gadget scanner that we implemented. It looks like this, which is very similar to the code that I showed you earlier. So now we have this mutex that we take. There's this, we free the object, then we set it to null, and then in the other thread we check whether it's set to null, and then we dereference it safely, right? Because there are mutexes. So there's no problem with this piece of code normally, but during speculation we can bypass it. So looking at this a little bit more in detail, as before, we would execute, so that's in green, architecturally until the K3, freeing the memory, but we would interrupt the thread just there. And then we would execute now speculatively, the mutex, bypass the branch during speculation, and then obtain speculative control for hijack. So this sounds easy, but in practice, I'm just going to mention one part of the attack here, but there's many other practical issues that one needs to solve for making that work. So to get first the thread to interrupt at the right point in time, we essentially set up a timer and time it such that it will hit the right window. But that's not so easy, because if you look at the piece of code in assembly, that's like 8 instructions, or at least it looks not so easy at first. But then if you look more in detail, you realize that the code that precedes it, which is many instructions, you can see there are many calls before, are actually under non-interruptible context. So that means that if we send our timer interrupt, it will be pending until this terminates, which means that we have actually a fairly big window to hit the timer at first. But that's not necessarily enough, because after that we still want to have our whole attack fitting inside of the window. So what we do is essentially to have additional IPIs, interrupts that we send, and we storm the CPU with those interrupts, such that once the timer IPI hits, we can obtain unbounded architectural use after free window. So basically, the Linux kernel keeps processing our interrupts and is in a unbounded loop processing our interrupts, which gives us a window as long as we want to execute our attack, right? So that was one of the practical challenges among many other ones that we had to deal with. And so let me track back to the code here. So we come here, we interrupt using the technique that I mentioned before. And then when the other process executes speculatively, before doing that, we need to do essentially an allocation with an attacker-controlled object. So this is known techniques. For instance, you can use MSG, and then you can put inside of it the function pointer that you're interested. And this can be used during speculation. What's nice is that you can do this as many times as you want. After winning the race once, you can leak, because of the unbounded window, as many times as you want by executing the second thread as many times as you want as the attacker. And we have implemented this, and you can lead with that about at 12 kilobytes per second from the Linux kernel. All right. So yeah, as previously, you obtain speculative control for hijack. So you need to build a rob chain that will speculatively leak the data from the kernel. Yeah. So I want to go through 2 sets of conclusions. The first conclusions is from an attacker perspective. So what we saw today, that essentially if you're stuck with some memory exploitation problem, first, because of stack canaries, maybe you can think of using speculation. Of course, as any speculative execution attack, that means that you will only be able to leak data. You will not gain architectural arbitrary code execution from that directly, right? But leaking data might be enough to then escalate privileges and so on. So for instance, if you have credentials or SSH keys or things like that, right? Similarly, when we think about speculative execution attacks, so for instance, finding gadgets can be very hard for SpecV1, but if we combine them with memory errors, can be much easier and we can have much more options. So we've seen that we can bypass memory-safe languages, at least in some contexts, right? Hardening solutions such as stack canaries and control flow integrity, and also synchronization mechanisms to then obtain speculative control flow, speculative concurrent use after freeze. What does it mean if we put our defender hat back on? There are essentially three solutions to this problem as a whole, and I have my preference among them. The first one would be to think about preventing speculation, the sources of speculation. So we talked about, for instance, conditional branch misprediction. Maybe we can prevent those type of issues from happening. And there were many microarchitectural level solutions that were proposed. So for instance, there are papers NTT, Dolma that one can look at, very interesting solutions. There are also program level solutions, many of which have been implemented today. So you can put serialization barriers. You can put branch condition dependencies, such as done by speculative load hardening, which is a LLVM plugin. But the problem with all of these is that essentially they all incur quite significant performance overhead if you use them indiscriminately. And that's not an option in practice because there are many threat models where these attacks are not feasible. So you might want to prioritize in those threat models performance over security. And so they need to be performed selectively on the right points in time inside of the code, at least to be effective and not incur too much performance overhead. The second option would be to prevent covert channels themselves. And I think this is even less of a good idea because there are too many covert channels to prevent. Although everyone has been at first using cache attacks to leak the data once they obtain speculation. So this led to people proposing defenses such as rolling back the cache state when we realize that we have a misprediction. That's not sufficient because we can find many other ways of leaking data. So for instance, in the SMoTherSpectre paper, we demonstrated that you can use port contention during speculation to then leak data. And in fact, in that case, there's no rollback that you can imagine because you're basically leaking during speculation, right? So impossible to roll back in that scenario. Another option is in our double BTI attack, we used the branch target buffer itself. So you can encode the information to leak inside of the branch target buffer during speculation because you can update the branch target buffer during speculation. So you can use many microarchitectural components in order to leak data. So it's a little bit hopeless as a defender to think that we can prevent those covered channels. So the third option, which is my favorite one, or the one that I really like and that people have already also proposed in many instances, is to essentially segregate secrets. So the reason why that is so powerful is that the only thing that we can ever do with these attacks is to access data arbitrarily, but not to, let's say, affect integrity in a meaningful manner. So if we had a way of separating the secrets from inside of our programs, there would never be anything to leak. So that's a very strong mitigation, if possible. And it is indeed possible. So for instance, a little bug there, but there was this paper called Secret-Free Hypervisors from Microsoft Research. And nowadays, this has been also, or a version of this has been implemented, also with address space isolation, for instance, for the KVM hypervisor. The idea being that, for instance, the guest memory has no business being mapped inside of the hypervisor, so then you cannot leak data. So this is applied to the hypervisor, but actually we would need that across all of the layers, right? So there are also secrets inside of the OS kernel. There are also secrets inside of programs, and what you call secret can be many, many different things. So actually implementing such a mechanism across the stack is very challenging, but I think it is something that's doable and would lead to a solution that does not have high performance impact. So that's the one that I personally like. All right, so this concludes the talk. Here are some references for the paper that I mentioned before, and I would be happy to take any questions. Everything, yes.
So you mentioned that for LLVM, CMI, you could not bypass?
Yes.
Was there, I think you mentioned briefly, was there a fundamental reason that you couldn't do LLVM CMI? And then it's something you could generalize towards other CMI solutions. So could you use the same technique?
Yeah. Right. Yeah, great question. So actually the issue was related to the speculation window, meaning the thing that we needed to evict would have led to the data that we want to overwrite to be also evicted, which is basically not possible, because then we don't get our control flow hijack. They did not design the system thinking of this attack, but it just so happened to be that indeed it was working. So does that fundamentally prevent the attack? Maybe not necessarily, if you can find another way of prolonging the speculation window. So for instance, some people have proposed port contention as one way of prolonging because the speculation will occur also in that case, but it's so short that you cannot even fit one node, let's say. So it's not, in practice, it's not exploitable. So that's what we meant for LLVM CFI. For GCC VTV, I think it could, in theory, be possible, of course, but it would need a significant redesign of how they store, basically, the information that they look up. But it's a good point and something that people use when designing defenses to make such attacks impractical, I think. Yep. Okay, so I didn't get everything, but I think the question reaches out to me, no. But so the question is, okay, are these attacks really happening in the wild? Are we aware of any such attacks? And is this something, I think the implied question, is this something we should really care, or is this just some, it's fair enough, I think, as a question to ask, or is it purely some academic exercise? So I think, from my perspective, there are very much feasible, realistic attacks. We've also seen, earlier in this conference, there was a presentation on the RAIN project with L1TF reloaded, which showed that you can use that to leak data from cloud providers, right? So that's a real impactful attack, for example. And I think, so part of the reason we don't see maybe so often is that there are easier things that you can do, right? So combining memory error exploitation with speculative execution is more tricky. As you've seen in the Ghostrace case, right now you need to not only raise the exploitation window of the raise condition, but also you need now to take care of the speculation window. You need to take care of more things. So this makes the attack more complex, that's for sure. Does that mean that attackers don't use it? I don't think so. At least there's this, if you look at the US government's vulnerability equities process, that basically says, the more complex an attack is, or the least complex an attack is, the more likely it is that they will disclose it instead of keeping it for offensive reasons, right? So that means that if you have more complex attack that they think fewer people will be able to exploit, it's more likely to be actually exploited and you will never hear about. So it's at least a way of looking at it. I don't know exactly what people are really doing in practice, right? Yeah, absolutely. I think a lot of people ask this question for good reasons. We should ask ourselves this question. I cannot really answer it because I'm not necessarily aware of any such attacks.
All right. Oh, there's one more good question. Maybe last two questions. Yeah. So thank you so much for the presentation. A lot of the gadgets you're talking about,
yeah,
especially, seems like they're very microarchitecture specific, right? Like gadgets themselves might change on different microarchitectures. I wonder, are there automated ways of finding these gadgets on a given architecture?
Yeah, so depending on the type of attack, you have different patterns that you will be looking at. Some of them will be more microarchitecture specific, some of them less. So for instance, in Ghostrace, it's actually not so microarchitecture specific for speculative control for hijack, as long as the microarchitecture allows you, that, which makes sense, right? There's no point in serializing the mutex there. You would just hurt your performance. So it will be the same on many architectures, right? So you don't need to do it in an architecture-dependent way, the search. In other contexts, of course, when you're looking at especially more attacks from the Meltdown family, that's going to be more microarchitecture specific. But yeah, hope this answers a little bit. There's also another aspect which is related to mitigations, I guess, because that's also quite microarchitecture specific. Yeah.